Hello friends, already in my previous video I have discussed about NAND SR latch. Okay, so this was the summary. This is active low NAND SR latch and this is active high NAND SR latch. Okay, why this is called active low? So because whenever S, that is set of input of this SR latch, is 1, then Q of n plus 1 goes to 0, but generally we say whenever something is setted, then output should be 1, but this is in this table or in this circuit it is happening in the reverse, so that it is called active low NAND SR latch. And so that what we have done, just we have added one inverter to make it active high. Okay, so this was the summary. If you want to check the explanation, please go through the link given in the description. Now you know what is the notion of the NAND SR latch was. Basically we started with one bistable element, that is this one, where two inverters connected like this format. Okay, that is one output is connected to the input of the other NOT gate, and the output of the second NOT gate is again connected to the input of the first NOT gate. This cross coupled, you can say, this type of connection was there, and we have seen that this is bistable element. If Q is 1, it is 1 for as long as I want, and Q bar is 0, and if Q is 0, it is 0 as long as you want. Okay, so that, but the issue was that we cannot change these states. So that what scientists have done, they replace these simple inverters using NAND and NOR gate. Why NAND and NOR trial? Because whenever a new circuit comes, obviously better to try with some gates which is universal gate, because we can modify that logic gate and we can make some other gates. So that scientists tried with NAND and NOR. So they first replaced by NAND gate, which I have already explained how the circuit works. Now it's time to discuss that if these inverters are replaced by NOR gate, which is other universal gate, what happens and how to analyze the circuit. That's what I am going to discuss in this video. So how to analyze this type of circuits, first you should know from my previous video. If you know, well and good, no need to check, but if you don't know, I recommend you to please go through the link from the basics, because these concepts are very important for understanding the working of the sequential logic circuits. Okay, latches are basic, you can say that base of the sequential logic circuit. Okay, so let's discuss. So basically, before going to NOR SR latch, just have a quick recap of NOR gate truth table. Okay, so 0 0 0 1 1 0 1 1 4 input combinations for two input NOR gate, and see if 0 0 is the input, then output is 1 0 1 0 1 0 0 1 1 0. From this truth table it is clear that if at least one input for the NOR gate is 1, output will go to 0, right? See, you can see for the last three cases, and you can easily conclude. Similarly for NAND gate, as I have explained already earlier, that this is the truth table for NAND gate, and from the truth table of NAND gate it is clear, if at least one input is 0, output will be 1. Okay, so for NOR gate, if at least one input is 1, output will be 0. For NAND gate, if at least one input is 0, output will be 1. That is NAND and NOR like complement, okay, or reversed working. Obviously from the basic concept of digital logic design itself, you can say that NAND and NOR works like reverse fashion. So what scientist has done, SR latch using NOR gate, in SR latch using NOR gate circuit, first this was the NAND SR latch, where NAND is replaced by NOR gate and the circuit becomes this, that is S and R. These two NOR gates, Q and Q bar, are respective normal output and inverted output we are getting here. But the issue is that, as I told you, NOR and NAND works in reverse fashion, so that scientists prefer to make as they have replaced the as they have not hampered the left hand side of the circuit. So what they have done, they have made these outputs complement, okay, because NAND and NOR works in reverse fashion. So if this is the structure of the NAND, to make a reverse of the NAND, what they have done, for S NOR output it was given as Q bar, and for R NOR gate output it was given as Q. That is, normal output is taken from the NOR gate, in which we are providing R as or reset signal as input. Okay, but you know from the general flip-flop structure that generally we follow this configuration, that is there may be multiple inputs in the flip-flop, but in the upper portion there is normal output, in the lower portion there is inverted output. But is it following here also? No, in the upper portion we are getting inverted output, and in the lower portion we are getting what? Normal output. So the scientist has just flipped this circuit and we got this one, that is R, S, then Q, then Q bar. Okay, so this is the SR latch using NOR gate. You should understand, don't simply replace NAND by NOR and start analyzing the circuit. Try to understand what is happening, why this is happening, because NAND and NOR works in reverse fashion. So if this is the circuit for NAND, this must be the circuit for NOR gate. Okay, now we will start analyzing this circuit. Before starting the analyzation, see, one thing is clear, that as we know for NOR gate, if at least one input is 1, output will go to 0. So first we can easily conclude what may be the normal output and inverted output for the last 3 cases of the truth table, because in the last 3 cases at least one input among S and R is 1. Okay, so that let's start with S equal to 0 and R equal to 1. Okay, and let's see what happens. If S equal to 0, R equal to 1 is satisfied, that means the set input is 0 and R input is 1. Now no need to think about the second NOR gate, that is this one. Think about the first or the upper NOR gate. For this upper NOR gate at least one input is 1, so that no doubt output will go to 0, because we know from the basic concept of working of NOR gate that if at least one input is 1, output will go to 0. So the output, if R is equal to 1, is equal to 0, the output Q, that is normal output, will be 0. Now this 0 will come via this feedback path and will be input for this lower NOR gate, and you can see for this NOR gate which is situated below, there both the inputs are 0, and you can say from the truth table of NOR gate that if both the inputs are 0, output will be 1. So that obviously Q bar we are getting as 1. So here there is no disturbances there. Q is 0, Q bar is 1. As we know, normal output is inverted version of the second inverted output. Okay, that is this one. Q and Q bar must be complemented form, and here also we are getting that. So if S equal to 0, R equal to 1 is satisfied, we can get that output will be, normal output will be 0, and this is obviously clear. Like normally if we press reset button as R equal to 1, that means we are pressing reset button, so output should be 0, because the reset will clear everything. So from the basic concept itself, it is following the normal principle. Now let us consider the second case of the truth table, S equal to 1, R equal to 0, and this analysis will also be very simple. If S equal to 1, R equal to 0, no need to think for the upper NOR gate, because here one input is 0, but we know for the lower NOR gate at least one input is 1, so that without any much calculation or much thinking, we can say that Q bar, that is inverted output, will be 0, because for NOR gate if at least one input is 1, output will be 0. Now this 0 will go via this path as a feedback, and it will input in the upper NOR gate, and see for the upper NOR gate both the inputs are 0, so no doubt the output will be 1. So if set bit equal to, or you can say set is 1, reset is 0, obviously the output should go to high, because we are setting the output so that whatever we are getting here also. So in this case, S equal to 1, R equal to 0, the output, normal output Q will be 1. It is satisfying. Now go to the next case, S equal to 1, R equal to 1. If S equal to 1, R equal to 1 is satisfied, the analysis will be very simple, and you can see here, if S equal to 1, for the lower NOR gate, Q bar will be obviously 0, because for NOR gate if at least one input is 1, output will be 0, and for the upper NOR gate also no need to think much, as R equal to 1, at least one input is 1, output will be 0. So Q and Q bar simultaneously 0, and this makes one problem. As we know that Q is something and the complement of that bit may cannot be same, that is cannot be 0 or cannot be 1 simultaneously, but here it is not following the basic concept of digital electronics. Q and Q are simultaneously becoming same value, and that is 0, so that this is called forbidden region, and the designers never use this particular case. Okay, there is S equal to 1, R equal to 1 for this NOR SR latch. Now the time comes for the little bit thinking part, that is S equal to 0, R equal to 0, because for in these cases we cannot directly conclude what may be the possible output for the NOR gate, because for NOR gate if one input is 0 we cannot say what may be the possible output. We have to check what are the other inputs too. Like here you can see, for if you consider this combination 0 0 and 0 1, you just consider for both the case S equal to 0 but R equal to first 0 then 1, so that in the first case when 0 0 combination, what is the output for NOR gate? Output is 1. For 0 1 combination, output is 0, so that we cannot directly conclude from S set bit if one input is 0 what may be the possible output. We have to check the other inputs also. Okay, if it was NAND gate, then we can say that for NAND gate if at least one input is 0, output will be 0. Similarly for NOR gate, if at least one input is 1, output will be 0, but for NOR gate if at least one input is 0, then we cannot say what may be the possible output. We need to check other input combinations also, and let us try to understand what to do. So if S equal to 0, R equal to 0, suppose you consider the upper NOR gate R equal to 0, but we don't know what is the other input, so that we have to assume some value. Okay, and let us obviously, as Q and Q bar are 1 bit, so obviously we can assume either 0 or 1. So Qn is to denote the previous value of the output. Qn is 0 means Q bar of n is 1, and Q of n plus 1 basically to indicate what will be the future value of this latch. Now if you analyze very carefully, if you observe that first suppose let us take Qn equal to 0. Suppose previously somehow this Q, okay, was 0. If it was 0, then this 0 will come. Suppose let me write here, this is 0. Now this 0 will come via the feedback path, and this will come here. Now for the second NOR gate, what is happening? Both the inputs are 0. As both the inputs are 0 for this NOR gate, what will be the output? Output will be 1. Okay, as output, that is Q bar of n plus 1. This is Q bar of n plus 1. Okay, that is the future output I am telling, not the past output, because we have assumed what is the past value. Now we are calculating the future value with combination of past and present inputs. Okay, now this one Q bar of n plus 1 is 1. This one will come here, and for this NOR gate what we are getting, one input is 0, other input is 1. For this NOR gate, upper NOR gate, as at least one input is 1, no need to think much, that is Q of n plus 1 will be nothing but 1. Okay, so basically if as one input is 1, output will be 0. As you know, for the NOR gate, if at least one input is 1, output is 0. So what we are getting, we have assumed Qn equal to 0, and we are getting Q of n plus 1 as 0 and Q bar of n plus 1 as 1. Fine. Now let us check for the other cases. Let me erase this first to avoid confusion. Now if you observe, suppose let us assume Q of n was 1 previously. If Q of, this is Q of n plus 1, sorry, not minus 1. If Q of n was 1, this one was here, this one will come as feedback path and will arise here. And now what will happen for the lower NOR gate, one input is 0, other input is 1, so that Q bar of n plus 1 will be what? As for NOR gate, one input is 1, no need to think much, output will be 0. As this is 0, this 0 will go via this path, and for this upper NOR gate, both the inputs are 0, so that output will be Q of n plus 1, that is future output, future normal output will be nothing but 1. So we are getting as Qn or past output as 1, we are getting Q of n plus 1 as 1 also. So that what we are getting, that if qn or past normal output was 1, future normal output, that is q of n plus 1, is 1. If past output is 0, future output is also going to be 0. That is, it is holding this state, so that this is called no change condition, or it will basically hold the past values. If s equal to 0, r equal to 0 is satisfied, what will happen? That it will hold the previous value, it will make no change in the circuit. Now let me summarize the table. S and R, and here it is q of n plus n, or future output. I am considering normal output of the flip-flop, not the inverted one. And now if you consider, there are 4 possibilities of 2 combination SR latch: 0 0, then 0 1, then 1 0, then 1 1, as we know from the basic concept of DLD. Now if you write the conclusion for 0 0, what we are getting? For 0 0 we are getting no change. Okay, so no change. And for 0 1, as reset is 1, q of n plus 1 will be 0. If set is equal to 1, reset equal to 0, q of n plus 1 will be 1. If set equal to 1, r equal to 1, this is called forbidden region. Designer will not accept this region, they will not work with this. Here you can see, if s equal to 1, r equal to 1 is satisfied, both q and q bar as 0, or you can write basically q of n plus 1 as you are writing, basically this will be 0, but this region will not use, because simultaneously q and q are becoming same values. So this is the summary of the SR NOR latch, which is very important for the sequential logic circuit concepts. Okay, this is all for my this video. If you have any doubt, you can ask in the comment section, and to check my previous videos on NAND SR latch, please go through the link given in the description. Thank you for watching.